The first type of IMF that we'll go a little deeper into is a dispersion force. Sometimes it's called a London dispersion force, and there's other names that you may see if you look online or in textbooks. The dispersion or London dispersion forces are the preferred terms by chemists and by the AP test. These, although often thought of as the weakest and least important, are actually potentially the most important for two reasons. One, all molecules experience dispersion forces, and two, they can be stronger than any other types, and especially with large molecules, they play a very important role. So whether I have an atom, and this happens with the noble gases or any pure element, or a molecule, my electrons are in a constant state of motion. When I have a nonpolar molecule, I would say on average, the electrons, as they're buzzing around, are equally attracted to each nucleus, meaning on average, they are distributed equally. But at any given moment, the electrons may have shifted more one direction than the other. In a polar molecule, we say that there is an unequal attraction. One of the elements attracts it more strongly than the other, and in that case, it stays polar, or on average, there is a higher density on one side. Whether it's polar or non-polar overall, there's always going to be fluctuations and changes in where the electrons are at any given moment. Because they all have electrons, all of them will have that random motion that results in dispersion forces. This happens when we have a temporary dipole because of the motion of electrons. So right here is an example of a very simple non-polar molecule with just a few electrons. When I have a hydrogen molecule, I've got a proton and a proton with two electrons moving around that are holding my molecule together. On average, the electrons would not be more attracted to one than the other, but at any given moment, they're not necessarily exactly in the middle, or it's not a one-to-one ratio. If, as in this picture, the electrons are a little bit closer to the hydrogen on the left, that hydrogen would be temporarily partially negative. That's an instantaneous temporary dipole. The electron cloud being pulled more this way would mean that the other hydrogen's nucleus is a little bit bare, making it partially positive. So then I have a small, temporary, instantaneous dipole on my hydrogen molecule. That can then induce, and we used the word induced on the previous one, and we'll use it a lot here, or force a temporary dipole on another. The bare nucleus on this hydrogen attracts the electrons that were shared equally in the neighboring hydrogen molecule, pulling the electrons more to this side and then pulling them away from this side. So we had a random instantaneous dipole on one molecule, which induced one on another. Sometimes dispersion forces are called induced dipole to induced dipole, a temporary kind of forced charge causing another one. In that case, because I now have a negative and a positive, they stick together. I've used this on in the previous example, but rubbing a balloon on your head forces a charge on that. We say that that charge is somewhat temporary, but it's because the electrons moved onto there. But then when I stick that to the wall, it doesn't make the whole wall electrified, and you're not going to get electrocuted when you touch it, but it does cause the atoms within that to align a certain way. And when they're aligned that way, the balloon can stick there. We can do the same thing by temporarily magnetizing something like a paper clip. In all those cases, we've taken something that we define as having no charge and temporarily move the electrons to give them a charge. Hydrogen makes a very small dipole because we have very few electrons. But as I go to larger diatomic molecules, as I go to large atoms like a radon compared to a neon or helium, and as I go to larger molecules with even more atoms and electrons, that temporary dipole can become larger and larger. The bigger the partial charge, the bigger the value of Q in my Coulomb's law. So to come back here, All of these are thought of in terms of this. If I have a small temporary charge to another small temporary charge, I have a weak attraction between them. But as that becomes larger, as I have bigger temporary polarity, I can have a bigger dispersion force. A word we use to describe the size of dispersion force that we can create is polarizability. So it's a measure of the distortion of our electron cloud, or how polar I can make something that's nonpolar. Molecules that have more electrons can be pulled more or pushed more one way or the other. The bigger the electron cloud, the more polarizable. A lot of times you're encouraged, either by me, by the notes, by a question, or even by a textbook, to look at molar mass. Molar mass and mass is not polarizability, but bigger molar mass means molecules with more protons and electrons. So the more electrons we have with a bigger molecule, the more polarizable it is. Double and triple bonds also makes it more polarizable, and the more surface area you have, the more polarizable it can be. So to just kind of summarize this, dispersion forces are probably the most important, and if you're asked to list IMFs, you list this for everything because they occur between all molecules, because they all have electrons that can move. The dispersion force is an attraction between temporary dipoles, that happens because of that random electron motion. The more electrons that you have, the bigger the dipole, therefore the stronger the polarizability. And if you have a really large molecule, this dispersion force is probably going to be the strongest of your IMFs because of how polarizable that molecule can become.